Hello and welcome. So let me start with a quick reminder of this week's material. So this week we started talking about chapter 12 and we started talking about static equilibrium. And I also introduced you to elasticity and fracture on Monday. So we said for equilibrium, we basically had two conditions. One was the total force was supposed to be zero as a vectorial form, and two was total torque in a system was supposed to be zero. And in the case of force, we decompose force to its components, and we saw that each sum along each direction should be zero. And for torque, we said that axis you calculate the torque was arbitrary, so you could choose anything you want. So we saw some examples, and later I told you about equilibrium, and I told you about different kinds of equilibrium. Basically, there was like stable equilibrium if the equilibrium you are in was stable to small perturbations. If not, it was unstable equilibrium. And we also saw like neutral equilibrium, like in this case, where small perturbations were neither stable nor unstable. And I also introduced a little bit of elasticity, stress, strain, and I showed you Young modulus, which was kind of like a spring constant for like tension, if you like, or maybe like inverse spring constant, or this E in this equation. And for a more general form, stress versus strain, we showed that this could be written as a slope of stress versus strain plot, which was kind of like this. And for shear, for forces that tries to shear the body, we introduce a different kind of modulus, and we call it, or like if you like a spring constant, we call it shear modulus. And for deformations in like a 3-dimension, for volumetric deformations, we introduce this kind of equation, and we introduce bulk modulus. And today I also suggested problems. Here's the problem. Approximately what magnitude force F sub m must the exterior muscle in the upper arm exert on the lower arm to hold a 7.3 kg shot put like this. Assume the lower arm has a mass of 2.3 kg and its center of gravity is 12 centimeters from the elbow joint pivot. Like this muscle is connected to this little region, and the center of gravity of this arm is somewhere over here, 12 centimeters, and there's this spherical object shot put in the hand, and we want to calculate what this Fm is. Let me give you a couple of minutes. How should I start? Free body diagram. Okay, all right, let me do that. So this force M is already here, so I'm not going to plot this. There is like some mass of arm times G here. And there is like this, let's call this mass of shot put times G here. So this distance is given to be 12 centimeters, and the other distances are given. Okay, I think this is all. Can we take torque with respect to elbow joint? Yes, let's do that. So total torque is 0, and I choose the elbow joint to calculate this torque. So if it is 0, I can immediately jump into this equation. So this F sub m times 2.5 centimeter should be equal to what? It should be equal to this torque, which is MA times G times 12 centimeters plus MS times G times 30 centimeters. Okay, I think that's all I need to find f sub m. From this f sub m, maybe I can calculate it immediately here. 966.6. Did anybody else get this number? 966, maybe 67. 967 Newton. Yes. Okay, thank you. Correct. Good. So I want to ask you, so I didn't convert this centimeter or here to proper units. Does Fn has any torque? Where is Fn? What is Fn here? Between the ball and the hand. Yeah, good point. So yes, like what we saw last week was when we were calculating torque, the internal torque was not important. We were only looking at external forces and external torques. So you are absolutely right. The ball is exerting some force on the hand, and the hand is exerting some force on the ball, but this is completely internal. So we consider the arm and the ball as a system, and we are identifying the forces, external forces acting on this system. So about this question, why didn't I convert centimeter here to meter? Is that wrong? Did I get the wrong result here? Yes, I mean, you can think of like a conversion factor multiplying all of these terms. I don't know, it's like 10 to the minus 3, 10 to the minus 3, 10 to the minus 3, but they cancel anyways, so I didn't convert. Okay, maybe I can continue. So is the next problem, maybe a shop sign weighing 215 Newton is supported by a uniform 155 Newton beam as shown in this figure. Find the tension in the guide wire and the horizontal and vertical forces exerted by the hinge on the beam here. This is sign, there's some beam, and we'll like to find the tension here and force on the hinge. Free body diagram. All right, let's do that. So first of all, there is this thing pulling down, but of course you can play the game T blah blah, but I think it's going to be like the mass of this shop sign. So I'm going to call it shop sign times G. And there is like somewhere in between here, I guess this beam has some M beam times G. So here there is like T, and there is like hinge force on the hinge, and I want to break it into its components. This one and this one. So F hinge, maybe I can just call it F because there is no other F here. So this is F Y, this is F X. Good, right? I got the free body diagram. What's next? Then the total torque is 0. Thank you. So the total torque, I think I can calculate it with respect to any point, but maybe I can start with this point. I can calculate the torque with respect to this point and see what happens. So the total torque is 0. Then, okay, I can call this distance. I don't want to write this. So this is L over 2. This is L over 2. And maybe I can write it, but that's fine. So MB times G is given. Okay, maybe I can write MB times G times L over 2 plus M S times G times L should be equal to T times, if this distance is X, I can just call it X. I know what X is, times sine theta. So this X is 135 meters. This theta is 35 degrees. This L is, I think, 170 meters. This MBG is what? MB times G is 155. And this one is 215 Newton. Now I can solve it for T. So T is equal to, I think it is going to be 0.5 MB plus, okay, maybe I can, because the given numbers are not MBG plus MSG divided by X times sine theta times L. So let me put these numbers. It's equal to 642 Newton. This is equal to 642. Let me look at the digits. Yeah, Newton. So I found 642. Maybe I can check. Can somebody else also do this? Just to make sure we got the right result. Majority says 642, so it is 642. So we found the tension in the guy wire, the horizontal and vertical force exerted by the hinge. So how do I do this? What is Fx and what is Fy? We can calculate the X component of the tension. Yes. So if we look at the components, this component can only be balanced by X component of tension. So we can use this to calculate Fx. So Fx is basically T times cosine theta. But I know T, let's just put the numbers. It's like this times 35 cosine. It's like 526. Found here 526. Maybe look at the digits. Yes. This is Newton. And I can do the same thing for Y component. But now Y component, so this component plus this component of T should balance this plus this, right? This is basic Newton's law, total force on the system. So then I can just write Fy should be equal to mb times G plus ms times G minus T sine theta. And I know all these numbers. Let's calculate. 1.776, maybe 1.8, which is rather small, 1.8 Newton. Next question. Okay, this guy. So a uniform rod AB of length 5 meter and mass m is equal to 3.8 kg is hinged at A and held in equilibrium by a light cord, I think massless cord, as shown in figure 64. A load W equal to 22 Newton hangs from the rod at a distance x so that the tension in the cord is 85 Newton. A, draw a free body diagram for the rod. B, determine the vertical and horizontal forces on the rod exerted by the hinge. And C, determine D from the appropriate torque equation. a lot of things, but I think we can do this. Maybe I can start with the free body diagram. Let me draw. So it's going to be something like that. Let's say this is rod. So, okay. So there is obviously M rod times G. There is some force here, F. And here, there's some tension, T. And is T given? I think it's not. Okay. And there is a force on the hinge. So I think I can just call this, so F, Y, and F, X. Any objections? Is that correct? Did I miss anybody here? Probably not, right? So what is F? I don't know. Oh, this F is given, yes. So this F is given to be, okay, this is actually W. And this one is given to be 22 Newton. So this one is given, this one is given. So we know these. T is also given. I didn't see. Okay, this is also 85. That's nice. So this is also given. All right. How do I start? What's the most economical way for me to get all these things? Total torque. Okay, let me jump into that then. I'll calculate the torque with respect to here. How can I do this? Let's do this way. So this angle is 53. Then this angle is also 53. Then this perpendicular here is, this is 90 minus 53. So, and okay, maybe this is, so this is 90 minus 53. This is also 90 minus 53. And here I need to calculate this one too, right? This guy has like, this is T, this has one component like this, the other like this. Obviously this one will have no torque, but this one will. So I need to calculate this component. For that, I need to calculate this angle. So maybe I can draw like a solid line from here like this. Right? Something like that. So I know if this one is 53, this one is also 53, then here this little angle is 53 minus 37 then. And the perpendicular is here, is calculated with respect to that angle. So maybe I can write, so total torque should be 0, then, so W times, okay, I have a lot of angles, W times, let's call D times, so this is, I need to calculate this component, so this is cosine of this angle, is sine of this angle, so this is sine 53. plus 1/2 L times mr times g times, again, the same angle, sine 53. Okay, these are angles. Should be equal to L times T times sine of 53 minus 37, right? So here everything is given except D, so I can find what D is, right? So W, M, all of them are known. So let me do this. So first, maybe I can pull it this side. So L, okay, times T. From here, D is equal to 2.43 meter. Okay. So I think I did what you asked, and I actually found the last C, question C. We got question A, and we are left with question B. So this is A, this is C. How about B? 2.4. Good. I also found 2.4. That's good news. Let me write it. 2.4 meter. How about B? How do I solve for B? Determine the vertical and horizontal forces on the rod exerted by the hinge. I need to find this component and this component. Rope's horizontal component, Fx. Okay. So basically, yes, what you are saying is, so that's the only force with the horizontal component. So if I find this, it's going to be equal to this. Or if I find this component of this will be equal to this, because there's no other option. But this angle here is, okay, what is that angle? This one is 37, then this one is 90 minus 37. Then I can just write this equation as, so Fx should be equal to T times cosine of this angle is sine of the other angle, so it's like sine 37, and it should be equal to, clear, so 37 sine is equal to this times T is 85, 51. I found 51 point, maybe 1. I'll just write 51 Newton. Okay. How about the other one? I'm only left with this guy. Sum of the forces and axis is equal. Okay, let me do that too then. So then Fy should be equal to W plus mr times G minus T times, okay, sine of this angle is cosine of this angle, cosine 37 degrees. I think we all know all of these. So let me calculate. W is 85 plus is equal to, I found minus 8.6. This is minus 8.6 Newton. And we know how to interpret these minuses, right? This minus just means I draw it in the wrong direction, so it should be like this. Okay. So a uniform ladder of mass m and length l leans at an angle theta against a frictionless wall. If the coefficient of static friction between the ladder and the ground is mu of s, determine the formula for the minimum angle at which the ladder will not slip. Forgot diagram? Yes, let me do that. So here there is obviously some force pulling it down, and ladder times g. There is a normal force here. So this is F normal. So there is a friction force here like this, F friction. And finally, there is normal force on the wall. Maybe I can call it FW for the wall. Is that it? Did I miss anything here? Everybody's here, right? Okay. Next, Fw is equal to friction. Yes, okay. So along the horizontal direction, I don't have many options. There's this guy and this guy. So I can just write Fw should be F friction, but we know what this is equal to. This is mu s times m ladder times g. Next. So similarly, I think I can write this one. F normal has no, I actually use this, but F normal has no other option but M ladder G. So this is the force in this direction. We got force in this direction. And last thing is obviously torque. And I'll calculate the torque with respect to this point. And let's do this. Torque should be 0. Then, okay. I need to do a little bit geometry. So this angle, if this is theta, this is theta. And this one is what? I feel like this one should also be theta, right? So this is 90 minus theta. This one is theta. Okay, this one is 90 minus theta. So if I sum these up, m ladder times g times L over 2 should be equal to F W times L times cosine of 90 minus theta is sine of theta. Clean up L, then W is equal to, oh, I think I forgot F factor of cosine here. So I need to, this is like a cosine of theta. So Fw is 1/2 m ladder times g divided by, I think it'll be tangent theta. I can put this back in here. And 1/2 m ladder g divided by tangent is equal to mu s m ladder g, m ladder g, then tangent is equal to 1 over 2 s, then theta is inverse tangent 1 over 2 s. Okay, that's it. Any objections? Any comments? I think that's it for me then. Thanks for coming. Thank you, everybody. I think I'll see you guys next week.